Okay, right. So back to my question. We know quicksort, for example, is n squared because you're right, right? Like you could be really unlucky with the pivots, right? Even if the quicksort algorithm tries not to, right? It's okay, I don't want to say it's difficult because that's not very true. But without modifying the algorithm, like the original quicksort algorithm that you guys were taught, if it was unlucky somehow, right? It says, okay, I'm just gonna pick some pivot and I'm gonna try, right? If you're unlucky, you're going to always pick like roughly the smallest of the largest element, and then your recursion becomes very lopsided, and you have to run partition like many times for you to eventually sort the input, right? So randomized quicksort is a way to deal with this. And what randomized quicksort says is that I'm not just going to, okay, so when I say worst case, what does that mean? That means that I know how my algorithm behaves, right? I know my algorithm is going to do this very specific thing. So if I give it this very specific input, it's going to take n squared time, right? So like as the input grows larger, I always can give it like an input where I force it to run an n squared time, right? Now what randomized quicksort does is randomized quicksort actually randomly picks a pivot. Okay, so what this means is that for you as an adversary, right, you can't give it any input and say, I know for sure the algorithm is going to run in n squared time on this input. Does that make sense? So like pretend you had a server, right, and all the server does is sort numbers, right? And maybe I don't like your server and I want to bring your server down, or I want to increase your electricity bill, right? So in other words, I'm gonna give it problems that are difficult to, I don't say difficult to compute, but it takes a long time to compute, right? So let's say I want you to lose money. All I have to do is just, if I know your quicksort algorithm, right, I know how your quicksort algorithm is choosing the pivots, right? And of course, like you could have like some way of choosing the pivots, like, okay, I'm going to pick the second element of the array, or like, I'm going to pick the first element of the array, I'm going to pick the fifth element of the array, or the 10th element of the array, whatever. I know how your algorithm is going to pick the pivots because you don't randomize it, like if it's a fixed algorithm, right? So then what's going to happen is that I can always give it inputs, right, that will make it run slow. Okay, so the nice thing about randomization, right, which is why we care and talk about it. Okay, the nice thing about randomization is that you prevent people from trying to force the worst case, like trying to force the worst case on your algorithm. So when randomized quicksort says, okay, screw it, I'm just going to randomly pick pivots instead, right? What's going to happen is that no matter what input I give you, right, I have no control over how the pivots are being picked anymore. And technically, frankly, you as the writer of the algorithm also have no control over how the pivots are being picked, right? So no matter what sequence of numbers I give it, right, because it picks the pivots at random, right, intuitively, that should have pivot, you should roughly end up with pivots that are usually in the middle, okay? So you should hope to see that the runtime is n log n instead of n squared, right? Of course, there is still a very small chance that your algorithm is very unlucky and it picks the wrong pivot still. But because it's now randomized, the point is that I can't force worst cases on it, right? So this is one reason why we study randomized algorithms, which is some of the stuff I want to show you today, right? So my plan, okay, this whole quicksort thing, right? I know I'm being very vague about it now, but next week I'll show you guys how to prove it, how to prove that if you randomize quicksort, right, it'll be good, like it'll run in n log n time, right? And it'll be very unlikely that it runs in n squared. Okay. So, but I don't have time to do it today, I don't think. So what I'm planning to do for this week and the next tutorial, okay, like for today, I'm going to show you some basic definitions from probability and statistics, right? So unless all of you guys, like all 19 of you, are actually okay with it, then we can skip it and I can just jump straight into the interesting stuff. But I think like maybe it'd be good if we do a bit of revision. I'll show you guys some basic definitions, and if I have time, I'll show you guys one or two different problems. All right, in the context of CS, right? Because like even if you guys have taken probability and stats, I'm guessing that people usually like they'll give you like the, they'll tell you oh compute this number or compute that number or whatever. What's the probability this happens? And it has like zero regard for CS, right? So like you guys might not know why you're doing it. Okay, so most of the stuff that I say here applies to randomized algorithms, except if you're doing AI and machine learning, because I don't do any of that stuff. So some of the stuff I say here would be like kind of applicable, but not completely. So, but I am teaching 3230, not 3244 or whatever. So I'll leave that to you guys to figure out. All right. So let me begin. So So usually for today and tomorrow, right? If I say X, for example, or Y in like uppercase, okay, what this means is these are usually what I'm gonna refer to as random variables. Okay, so a random variable is basically just think of it as a variable, and what does a variable mean? A variable means that it could take on possibly different values, right? Okay, I could have random variables that, for example, let me just get this question out of the way. Can I have a random variable that always returns me 100? Like I said, this random variable, I define it as 100. Yeah, you can. It's completely fine. It's just not very random, so we usually don't care much about it. Okay, so what is a random variable? You can think of it as an object where if you poke it and say, hey, can you give me a number, right? You'll say sure, okay, but it might not give you a fixed number. It might give you like different numbers. Like for example, a random variable could give you numbers 1, 2, 3, 4, 5, and 6, right? And maybe with some probability, right? So that maybe, for example, probability 1/6, 1/6, 1/6, like maybe all of these guys 1/6, right? This is just like your dice, right? And you know, a dice is the thing that happens in real life, but we want to be able to mathematically express that somehow, right? So this is how you go about expressing it. You would say, okay, I have a random variable, it can give me some value, and it gives me some value with some probability. Okay, so in other words, what I'm saying is that a random variable gives you like some value that you want with probability like something. Let's call that P, like yeah, PI or whatever. I mean, sorry, like yeah, I don't know, whatever. Okay. So the nice thing about this is that using this sort of like notation and this sort of framework, we can now sort of like talk about coin flips, right? Like a coin flip, for example, could be one or zero. Let's say one with probability half, one with probability zero with probability half. This would be a fair coin, right? Maybe you can think of a bias coin where it gives you one with probability 1/3 and gives you zero with probability 2/3, right? That's also a coin. That's also a coin as well, right? So these aren't horribly interesting, but this is roughly what you're dealing with. All right. So intuitively, you think of a random variable as a box. Okay. And in this box, right now, you don't know what value it contains. Okay. So you have to ask it for a value. Right. And you know that a third of the time you should see one, like, you know, zero, like 2/3 of the time you should see zero. Like if this was the coin that we're talking about, for example. Right. So that's the intuition behind a random variable. For those of you who've seen it before, again, like, you know, you might be wondering, why do we need this, right? Like it'll become like quite clear like soon, like at the end, like in the second half of the tutorial. I just want to get all the definitions out of the way first. Okay, so now I've defined a random variable. That's not horribly interesting by itself. You know, all I've said is, okay, you have a black box and it gives you a value, right? But I've not shown you what we can do with it. All right. So there are a few things I want to mention. So let me list them out here, because I always forget. I need to talk about E of X. I need to talk about LOE. I need to talk about expectation of F of X. Okay. These are the things that we care about for today. Are there more? There might be one or two more, but anyway, screw it. Let's talk about these. Okay. So one thing that we care about, right, is what's the expected value. So think about this as like, if let's say you and your friend are playing a game, okay, and he comes to you and says, I have a coin, okay, and here's how we're gonna play it. If the coin tips heads, right, you win, you get money, I pay you $1. And if the coin says tails, I win, you give me $1, right? Okay. So how can we phrase that? So we know that a coin, we know that there's a coin, let's say X, right? And I know that it gives me hits with probability half and tails with probability half. Let's say it's a fair coin for now, right? And if it's hits, you should be winning $1, and if it's tails, you should be losing $1, right? So this is what the coin looks like. So one question that you might ask is, right, like at every round, right, like how much do I expect to win? And intuitively, of course, you would feel like the answer is 0, right? Because it's a fair coin. It could go either way, right? So how do you formalize that? So we call it an expectation, which is the value that we hope to see or that we expect to see. I don't know. I hope and expectation might not be the same thing in English, right? Because like, you know, you should like hope for the best but expect the worst or whatever. Yeah. Anyway, like we're not here about like English. So this is the value that you should be expecting to see. Right. So how should you like formalize this notion of, oh, I shouldn't be really winning or losing, right? Well, the way that you would think about it is that expectation of X here should be given as let me write the general form first. So I would say summation of I, okay, and like I times the probability of X equals to I. So what's the intuition behind this summation? All this summation is saying is that I'm going to go through all the possible values that the random variable X can give me. Okay, in this case, right, it's going to go through two possible values. It's going to go through -1 and it's going to go through +1, right? These are the only two values that x can return me in this example. Okay, so what's the probability that x gives me -1? Well, that's going to happen with half, right? So the probability that x is equals to -1, well, this is a half, and the probability that x is equals to 1 is also a half, right? So you just multiply these two things in, -1 times a half plus 1 times a half. This just gives me 0. Okay. So what this means is that, you know, like every round we expect to not really win or lose money. That's not true, right? Because every round either someone wins or someone loses, right? So it's kind of weird to say that every round you don't lose or win, right? Because every round, no matter what happens, you like when the round is over, you have to pay him or he has to pay you, right? So what do we really mean by this? What we mean to say is that if you tried this many times, right? If you tried, like say for example, you didn't play one round, you played like 100 rounds, right? At the end of the day, it's more likely that you will not, like, you know, it's more likely that like no one's money changes. That's what you should hope. Like that's what you should expect to see. And if you play like 3 rounds, for example, I mean, maybe the same thing happens, right? Like, yeah, but the point, that's what I'm trying to get at. It may not be true, right? It may be that you're really unlucky or you're really lucky and like you actually end up winning some amount of money. But, you know, you shouldn't really expect it. All right. So maybe this is not very pronounced in a fat coin. Let's say the coin now is tipped against you, right? So like you have a coin that gives you heads with probability 1/3 and tails with probability 2/3. So this coin is in the favor of your friend, right? Which is kind of expected. He came to you proposing this gamble, so obviously he should have a coin that is in his favor. House advantage, right? So if you had such a coin, right? Think about what happens if you played with him for like 100 rounds, right? Or like let's say 300 rounds. So after 300 rounds, right? After 300 tries, you should kind of expect to be like, you know, like short of like $100 or something, right? Because what you should expect to see is that a third of those 300 coin flips, sorry, it should not be 100, right? It should be something else. No, it should be 100. Yeah. Because for a third of those coin flips, you win $100, right? And for 2/3 of the coin flips, you're going to have to pay him like you know, $200, right? Sorry, for each of the coin flips you play $1. So like out of like the 300 coin flips, you're gonna end up like winning $100, but you're gonna end up paying $200, right? So you should expect to be $100 short. So in other words, you shouldn't play this game. Okay. Well, you know, that should be kind of obvious, but so this is roughly what expectation looks like. Okay, like I know it still all looks like math right now, right? It does not look applicable to CS yet. We'll get to that in a bit. All right, so just bear this in mind. Okay, so what's the intuition? Like even if this was a dice, right? The intuition is just that, okay, what values should I hope to see? What's the rough average, right? You take all the values, you multiply them with the probability that you get that value. You add them all up. That's what you should expect to see. Okay. Okay, let's talk about linearity expectation next. So fine, you know, I've shown you how to get expectation for random variable x. I've shown you how to get an expectation for random variable y. I mean, like, you know, like separately, right? But random variable y is just like random variable x, right? It's just a different label. Okay, now, let's say we modify the game a bit, right? And we say, okay, we're going to play the game a bit differently now. You're going to flip a coin, I'm going to flip a coin. Okay, and you know, we'll play the same way, but like now, like, you know, like instead of just you flipping the coin and us paying money, I'll also flip a coin and you know, then you'll have to pay me money or whatever, right? So then the question becomes, well, how should you model the gains now, right? So you could think of this as perhaps maybe x plus y, right? So maybe this guy again is a random variable that gives you +1 or -1. This guy gives you a value of like +1 or -1, for example. Okay. So the total money that you would expect to win after one round, like, you know, that you would have after one round is just x plus y, right? Like maybe he flips his coin first, then either you pay him or he pays you, then you flip a coin, then either you pay him or he pays you, right? That sort of thing, right? Now the question is a bit more complicated, right? Like how much do you expect to win every round, right? So what we want is this, right? We want expectation of x plus y. Okay. Now, in general, right, in math, like in case you don't know, in math, right, it's not always true that you can just say, oh, this is like, if I have some function and I have like two variables, let's say x plus y, you know, like, and this is always equals to f of x plus, like, you know, f of y. That's not always true, right? Think about like your sine and cosine functions, for example. I'm pretty sure it's not true, right? Or a function like x squared, for example, this is definitely not true, right? But it just so happens that for expectation, it is true. right? You shouldn't take it for granted. That's what I'm trying to say, right? You should appreciate it, the fact that it's true. All right, and this like I told the previous class, this is the gravy train for CS. Like you get a lot of value out of this statement alone. Like I'll show you in a bit. All right. So this is one thing that this is one thing that you should know, right? So we call this the linearity of expectation. Okay. Now, this might feel obvious to you if X and Y don't depend on each other, right? Like for example, in this example that I've given you, you flip your coin, I flip my coin, X is doing its own thing, X as a random variable is doing its own thing, Y as a random variable is doing its own thing, right? But the thing is this, if let's say I had two random variables, X and Y, such that Y depends on X for some weird reason, like maybe X is something like a coin flip or a dice or whatever, and Y as a random variable is going to say, I'm going to wait for X to come out first, and whatever value X comes with, right, like comes out with, I'm going to do something different. Okay. Does that change the expectation? The answer is, does that change this statement? The answer is no. So this statement is true, even if X and Y depend on each other. I shouldn't say that, I should say like are not independent. Are not independent. Okay, so like when are two random variables independent? The two random variables are independent if X gives me a value, right? And it doesn't say anything about what's going to happen to Y. Okay, but when X gives me a value, it changes what Y does, right? That's when there is like some notion of non-independence, right? So you would expect that a summation like this, like you might not be able to break it nicely, right? Because this is like a statement about X. This is a statement about Y. So you might say, yeah, but if Y depends on X, how can you still break out the expectations? Well, if you work out the math, you'll see that it checks out. But I'm not a stats class, so I'm not going to prove it. You can look it up online. Right? The promise is that this happens, right? So no matter what you do, if you have two random variables, I don't care how you define them. Like as long as they're random variables, even if they depend on each other, you can break it up into these two sums, right? Or you can think of this coin flip example, like maybe, okay, depending on what your coin says, I'm going to do something different with my coin, right? This will still work out. This will still calculate the number of the expected number of money that you should win at that round. Okay, so the linearity of expectations is very magical, and we love it for that in CS actually. Okay, any questions before I move on? I know I'm going a bit fast, so if you guys have a question, you should ask before I start using these things. Because if not, I'm going to move on. Give you guys like 5 seconds to think about it. No? Okay. ask in the chat if you have a question later. Okay, so last one. Let's do this. Let's do this real quick. Okay, so expectation of f of x. Okay, so expectation of f of x is kind of like saying, okay, so let me talk about this a bit. If I have time, hopefully I'll be able to show this to you guys today, all right? Because I really want to show it to you guys. Let's say that I have a coin called X, and it gives me +1 or -1. Okay, now +1, let's say with probability half, -1 with probability half, right? So this is kind of like the gambling coin that we talked about, just the gambling outcome that we talked about just now, right? I actually need it for something else later on if I have time to show it. Okay, but one thing you should notice is that x squared is also a random variable. So how should you interpret this? What does x squared mean, right? X squared means that you're going to ask for a value from x first, right? X is going to feed you a value, right? So you poke at x as a black box, and x opens up and it says, okay, my value here is -1, let's say. Okay, you take that value that it gives you and then you square it. Okay, so if you did that, what's going to happen is that this value is going to just turn out to be, x is going to give you 1 with probability half. When it gives you 1, you take the 1 and you square it, right? So with probability half, you're given +1, then you square it. That's the outcome here. With probability half, right, you get -1, you take the -1, you square it, right? So x squared is a random variable that just returns you 1 with probability half and 1 with probability half. So this coin is not very useful, right? It just gives you 1. Okay. So it's still a random variable. It's just not very random, right? But what am I trying to tell you? I'm trying to tell you here, the way that you should think about it is that if I give you a random variable and I apply some function onto it, okay, what you should think about is you should think about it as you asking the random variable for a value and then multiplying it. Okay. So this is how you should see it. Okay, now the last thing that I want to talk about before I move on to the slightly more interesting stuff, which is very useful in CS, is what's the expectation of f of x, right? Like so in that example, for example, I would be asking what's the expectation of x squared. Okay. Now that one wasn't very difficult, right? Because x squared was a random variable that always gives you one, so the expectation is always one, right? So we don't even need to use any definitions for that. So like forget that. Let's do the general case. Now there's actually a name for this. There's actually a name for this law. So like whatever I'm telling you here is not actually very trivial. You actually need to prove it. I think for the discrete case it's easy, but for the continuous case, if any of you actually do like continuous like statistics, it's called the law of the unconscious statistician. You can look it up in your own time. I don't want to prove it. It has to do with like some convergence. Like you're not promised that like the integral converges or some stuff like that. But like in 3230, we don't really care about that. In AI, maybe you would. I'm not sure. So or machine learning, I don't know. Again, I don't do any of that stuff. So that's really up to you to go figure out to go learn and figure out, right? So over here, what should the expectation look like? Again, you should think of it as me summing across all the possible values that the random variable x can take. Right? The reason why, again, is because when you put random variable x, right, before you ask for a value, you're going to ask it and it's going to give you some value I with probability PR x equals I, right? Then what you're going to do is you're going to apply the function onto that value, right? So that's going to be f of I. So this is what your random variable looks like. Okay. I know this all looks very abstract for now, like, like maybe like a bit like you've never seen this before and a bit inapplicable, but trust me, it's useful. So I'll either show it to you this week or next week, depending on whether I have time. Right? And there's like a really cool magic trick you can do with this. Oh, well, really cool magic trick is subjective, right? Like if you think like okay, never mind. I'll show you guys if I have time. Okay, let me quickly finish up the last few things. All right. So these are the basic definitions. Okay. Let me introduce to you two things that we love to do in CS. I mean, okay, two things that we love to use in CS. Sorry. Okay. So if I have a random variable x, okay, and it does this thing where it's 0 or 1. Okay, let's say with some probability p and 0 with probability 1 minus p. This kind of looks like a coin flip, but we have an actual name for it. We call it an indicator random variable. So indicator random variable. So random variable is know. So you just think of it as an indicator. So what do I mean when I say indicator? Think of this as like a flag. So if something happens, if something good happens, right, you'll say 1. You'll flag up and you'll say, oh, 1. If that thing doesn't happen, it won't raise the flag. It just say 0, right? So in CS, you're going to see like next week when I show you like the quicksort thing, right, that I mentioned, right, we're going to use a bunch of these to analyze the running time of quicksort. Okay, but the point here is that you should think of these as like counters. Let's say you want to count something good or something bad that happens, right? You'll use an indicator random variable. When the thing happens, it will flag up and say 1. Then you'll add it together, something like that, right? That's the rough intuition. Again, I don't have time to go into today. That's just me introducing it to you guys. So one thing that we care about is the expected value. So when I say E of x, right, what is this? This is going to be 1 times the probability that x is equals to 1 plus 0 times the probability that x is equals to 0, right? I know that by definition, this is 1 times p plus 0 times 1 minus p, right? But 0 times 1 minus p, this just becomes 0. So really the expectation of x, if it's an indicator random variable, is p. Okay? It's a bit weird, but that's all there is to it. Okay, so again, nothing horribly useful yet. I'm almost done. Last one. So the last, well, not really the last one is binomial, but we don't really care about binomial. Okay, so the last one is geometric. So geometric, right? You should think of this as a random variable. Think of a process, right, where you're gonna flip coins. Okay, and the way that it works is that you have a coin that gives you head with probability p and tails with probability 1 minus p. Okay, now the way that random variable x is going to work, let me define it as a process for you. Okay, I'm going to flip a coin. If the coin says heads, I stop. If the coin says tails, I move on. I continue the process. So if it says tails, I'll flip again. If it says tails, I'll flip again. If it says tails, I'll flip again. If it says heads, okay, I stop. Okay, so x here is going to be a random variable that tells you how many times you had to try before you stopped. Okay, so the probability that x is equals to I, what this means is the number of tries that you need, okay, is the same as 1 minus p to the power of I minus 1 times p, right? Because the probability that you need, let's say 1 round, right, means that you hit heads on the first try, right? So then you had no tails. So none of the 1 minus p and one of the p, right? If let's say it took you 100 tries, then for the first 99 tries, you must have hit 1 minus p, right? And then for the last try, you must have hit heads, right? So that's p. Okay. So this is a geometric random variable. Now, we usually don't really care about this value itself. What we actually really care about is the expected value. So the expected value for a geometric random variable is 1 over p. So let's try a few toy values just so that we're clear on the intuition. Okay, if let's say you have a fair coin, right? So a fair coin is what? It gives me heads with probability 1 over 2. It gives me tails with probability 1 over 2, right? What this says for you, right, is that if you try to do this process, you would expect to have 2 tries before the coin stops. Okay, so that's like that's like what you should hope to see. Okay, but if I had a coin, for example, that was a bit worse, right? Let's say the coin gives me heads with probability 1 over 100, right? Then you probably shouldn't hope to get a hit within 100 tries, right? I mean, I'm not saying it can't happen. It could happen. You could be extremely lucky, okay? But that's not what you should hope to see, right? So these kind of like values are good to sort of like say, okay, if I have these 2 coins, right, which one do I think should like finish faster? Which one do I think should, which one should I hope should finish faster? The expectation gives you a good sense of that, right? Okay, so I'm done with the definitions. Does anyone have any questions? Because all these things are just basically me giving stuff a name, like giving concepts a name. So I've not really done anything interesting right now. So if we're okay with the definitions, I'm going to move on to the algorithms. Okay, no one's saying anything. I hope that means we're all okay. Okay, yeah, no one's saying anything. Okay, let me talk about the first famous thing, which actually still happens in stats, but the coupon collector problem. Okay, I actually like only mentioned this in passing at the end of the previous class, but let me mention why it's useful in CS now, right? So that we at least care about the story I'm about to tell you guys. Oh, let me mention the problem first. So the story goes like this. Okay, every day you go to supermarket, and at checkout, like at the checkout, you get a coupon. You get a coupon of type I. Okay, and like let me just write here, like there are total of n types. Okay, and when I say you get a coupon of type I, this happens with probability, I should write it in blue, with probability 1 over n. Okay, so it doesn't care about what coupons you already have. It doesn't care about how many coupons you've taken out, right? Because let's say there are infinitely many coupons and they don't know what coupons you already have, right? So they'll just give you a random, like of all the n coupons, they just randomly pick one with so that happens with probability 1 over n, and they'll just give it to you. Okay. The question that I want to ask here is how many days before how many expected days? Like, okay, like I'm trying to like slot in expectation everywhere. In expectation, how many days before you get all coins? You get all coupons. You get all coupons. When I say got all, I mean like you get all types of coupons. Bad handwriting. Okay. Now let me briefly explain in like hopefully a minute why you might want to care about this. So I don't know if you guys heard of what's it called? Distributed algorithms, or like parallel algorithms, for example. So if you guys actually ever care about that, or if you guys actually ever want to take the module, which go for it. We have one in our school. I mean, like your school, not my school anymore. Where they talk about, let's say I have like all these like n distributed nodes, okay, and like they're on a ring, like a ring network. So what I mean by ring network is that like for example, the way that they can communicate to each other is only via their left neighbor or their right neighbor, right? So everyone is put on a ring, they can't communicate across, for example, that sort of thing, okay? And let's say all of these nodes don't have an ID, or maybe they could have an ID, but it's like there's no guarantee the IDs are distinct. So each of these nodes, each of these processes like want to sort of elect a leader, and electing a leader in a distributed system is very useful because the leader could start doing good things, right? Could start allocating work. You could start making calls, right? Could start saying, okay, you this node do this, you this node do this, you this node do this, that sort of thing. Okay, so you want to have a way to pick a leader. Okay, and the difficult thing is that if you try to write a deterministic algorithm for this, right, you would fail. Meaning there is no way for you to write an algorithm that is not randomized, right? That doesn't fail. Okay, so the proof is a bit difficult, and it's not covered in 3230. I will not go through it. All right, just take my word for it. If you had a ring network, okay, and you have all these distributed nodes that want to elect a leader, you would fail for sure. Okay, and sort of like there's a randomized algorithm for this. So there is no deterministic algorithm, but there is a randomized algorithm that does this for you. Okay, and um, oh no, no, maybe you do have IDs. I'm not sure. Okay, I can't remember one of the few. But the point is that there is a way for you to elect a leader in a randomized fashion. All right, and what I'm going to say, like if you look at the algorithm, right, and you squint your eyes a bit, it's actually the coupon collector problem. Okay, depending on how you phrase it, you might not phrase it as a coupon collector problem, but you can, right? And then what would that tell you is something along the lines of, okay, so if I run this algorithm, it's randomized, okay, and it has to run potentially many rounds. And the question that you might want to ask is, how many rounds do I need to run this algorithm before we finally have a leader? And so that's the same as you asking over here, like in number of days, like how many days does my algorithm have to run? Like how many days do I need to come and collect the coupon before I have all the coupons, right? So that leader election thing kind of looks like coupon collector, right? So like if someone asks you, oh, you have this distributed algorithm, like, are you sure it will find the leader in time? You say, yeah, okay, don't worry, like I can prove to you that it will take at most how many rounds or whatever that is. All right. So that's one motivation why you could or should care about coupon collector. There are other examples in the wild, but that's the first I usually think of. Okay. So with that in mind, let's talk about this problem. Okay. Let's say you're an avid supermarket goer. Every day you go to the supermarket, right? At the checkout, they'll give you a coupon of type I, and you can't go to the cashier and say, hey, I want a specific type, right? They give you one of the n types with probability 1/n. Okay, and you want to ask yourself in expectation, how many days do you need before you see all the coupons, right? Because, and this is random, right? Because you could think that maybe you're very unlucky some days and they give you like coupons that you've always seen before, right? Sometimes maybe you're lucky, they give you a new coupon, Sometimes you're unlucky, they don't, right? So based on the definitions I've given you so far, right, there's still a lot of thinking required for you to get this done. Because it's not just a very simple, this is a geometric, this is an indicator random variable. Okay, let's just chuck this through and find the expectation. Nothing like that. There's actually a bit of thinking involved, right? So the first trick that I want to teach you today, okay, is well, let me go through them step by step. Okay, step one, what do we care about? Ask yourself, what's the quantity we care about? So in the question, right, what I'm saying is, in expectation, how many days do we need before we collect all the coupons, right? Fine, let's write that as a random variable. So D is a random variable. It can give me, this random variable is going to give me the number of days required to collect all the coupons. Okay, now it's not obvious that this is anything, right? Like it can't be a geometric, it's definitely not indicator random variable, and it can't be a geometric because geometric is all about coin flips, right? But this guy has like n different items and you don't know which of the n items are coming, like n different types of items, and you don't know which of the types of items are coming in at any given point in time, right? So you have like this, if you try to solve it like in a very brute force fashion, you have this very weird big tree that you need to deal with, right? Which is probably not very easy to deal with. So fine, that's fine. Let's just think of this as a random variable for now, and let's think about the process that happens. Okay, so let's say this is day one. Let's start with a blue day. Okay, now let's say on day one you had no coupons, right? So whatever they give you is definitely a new coupon. We know this for sure, right? So at day one you get a new coupon, right? Maybe at day two, perhaps you're still kind of lucky, like they give you a new coupon, right? And then maybe day three, for example, let me ask this. Let me ask this at first. So at day one you have no new coupons, right? So out of the n coupons that you have, right? You getting any coupon is considered a new coupon, right? So that's fine. But now you have one coupon in your bag, right? So I don't mean coupon one. I mean like one coupon in your bag. Okay. So the next day you try again, right? What's the probability you see a new coupon? Does anyone know? So again, let me repeat the question, right? On day one, I have no coupons. I go in, I buy something, they give me a coupon, right? I definitely will see one new coupon, right? I don't know what type the coupon is, that's fine. But I know that I'll see one new coupon, right? So like a coupon I've never seen before. So they give it to me, I collect it, right? That's fine. But on day two, right, when I go again, right, what's the probability they give me a new coupon that I've never seen before? I had n coupons that I cared about. That's right, n minus 1 over n, right? So why? Because this, I have one coupon that I care about. I don't care about it anymore. There are still n minus 1 coupons that I want, right? And this is out of the n coupons that I could possibly have, right? So the probability I see a new coupon now is n minus 1 over n, right? So maybe, okay, fine, you know, maybe on day 2, they still give me the same coupon, right? And okay, fine. Then on day 3, maybe they still give me the same coupon. I don't know. I'm just illustrating a process here, right? And maybe after that, on the next day, they finally give me the new coupon. Okay. So my question now is, right, what happens then? So now at this point, right, I have 2 new coupons, right? At this point I had 0, at this point I had one new coupon. So the next day I want to ask for a coupon, right? What's the probability that I see a new coupon? What should it be now? Now I have 2 coupons that I've seen. So in my bag I have 2 coupons, n minus 2 over n, that's right. So don't forget the parentheses, okay? I see some of you writing this, but like if you write this, right, like we'll think it's this, okay? So like don't forget the I know you guys know the answer. It's just don't forget to write the parentheses. I made that mistake in exam once and I lost the marks, you know. It was so sad. Okay, but right. So you have 2 coupons now that you don't care about them anymore. You want to see a new coupon. There are n minus 2 new coupons. You want one of them, right? And this happens with probably 1 over n for each of them. So there's n minus 2 over n, right? Okay, good. So you know, like maybe you try again, you know, and then like eventually you get a new coupon, right? So each of these times, right, when you're trying, like this here happens with probability. Okay, let me use green here. This happens with probability n over n, right? Over here, when you're trying, right, okay, like what happens here? Like you failed, right? Which means that you must have hit the old coupon, right? That happens with probability 1 over n, right? And you failed again, you must have hit with probability 1 over n, right? But over here, you succeed, right? So you got a new coupon. That happens with probability n minus 1 over n. Okay, now over here is a different story, right? So let me separate this into partitions. Now over here is a different story, right? Over here, what you would see is that this is over here, if you failed, it must have happened with probability 2 over n. This happens with probability 2 over n, right? And then like you succeeded, that must have happened with probability n minus 2 over n, right? So how long does this process repeats for? This thing goes on for as many different coupon types as you want, right? Until like eventually you hit the last one, right? Okay. Now if I were to try to express d as this value, so let me use this in purple. I think purple will make more sense here. If I try to express d as this value, right? You can think of this as a random variable that you can decompose this random variable. So you can think of this as, let's say, d1. So this here is d1, this here is d2, this here is d3, all the way until eventually at some point dn minus 1. Actually I should use 0, 1, 2, then dn minus 1. Yeah, correct. Okay, so what's the intuition here? I'm trying to decompose my big variable. My big variable counts the number of days, right? I'm saying, okay, think of every day, like think of this random variable as me partitioning up my days, right? Into asking, how many days do I need before I move on to the next stage, right? Now, within each stage, right, if you forget about the rest of the stages, just look within a single stage itself. This is a geometric, right? Do you see it? Because within a day, like, well, sorry, not within a day, within a section itself, right? You're asking, okay, I'm gonna keep trying. I'm gonna ask for a coupon. Right? If it gives me a coupon I've seen before, screw it. I need to ask again. If it gives me the same coupon I've seen before, screw it. I need to ask again. But the moment it gives me a new coupon, I'll say, I'm done. I'm moving on to the next stage. Right? So each of these d sub 0, d sub 1, d sub 2 values, d sub n minus 1 values, these are all geometrics. They are individually geometrics, right? And di, you can think of it as a geometric random variable, right? Where you've already seen I coupons. Okay, so what's the expected value of di? This is the expected number of days before you see a new coupon. Does it make sense? Right? So the expected, I know, is 1 over p, right? Where p is the probability that I succeed, right? Which happens to be 1 over n minus I over n, which is just n over n minus I. Right? Right. I hope this idea makes sense. Stop me if it doesn't make sense, because I'm going to keep moving. I might have time to cover the last like one more question. All right. So as in like one more example to show you guys. Okay, so let's write this down, right? The total number of days required is going to be the number of tries I need to make, right? From having seen no coupons to having seen n-1 coupons, right? Di, right? Now I don't know what this value is because it's a random variable, right? But I know that the expectation of D, right, is the expectation of this guy, right? Like this summation here, right? And since by linearity of expectation, which I showed you guys just now, is the same as the summation of the expectations of di. I is equals to 0 to n-1, right? So what is this? I know that expectation of di is n times n minus y. So this is n over n minus I. So this is just summation of I is equals to 0 to n minus 1 times n, sorry, like of this term, right? Now I can factor the n out. Now I get this. Okay. Now this summation might look weird, right? Because it's like, oh, I've never seen this sum before. Like, yeah, in like more, you know, I'm pretty sure you like most of us would not have seen this sum before, right? But think about what this sum looks like. When I is equals to 0, right? So let me write this here. So this is n times this summation, right? So when I is equals to 0, this is 1 over n minus 0, right? So that's just 1 over n, right? When I is equals to 1, this sum, the term is n minus 1. Well, what about at the end, right? At the end, right, it's n minus 1, right? So that becomes 1 over 1, right? Don't forget to flip the sign. Okay, so what is this? Well, summing forwards, right, is the same as summing backwards because addition is commutative. Okay, so this is n times the summation of 1 over I from I is equals to 1 until n. Right? Which gives me, this is harmonic. So if you remember, which I hope you remember, this is harmonic, right? So this is just n times like ln n plus O1, or I don't know. So there's like an additive term in there somewhere, but this is like roughly equals, this is very roughly equals to n times ln n. So this is like roughly n ln n. So what does this tell you? If the grocery store or the supermarket that you go to has 100 coupons, you should expect to take about 100 times on 100 days. If it has 50 coupons, you should expect to take 50 times on 50 days. That's that's a rough idea, right? So this roughly gives you a calculation on how many tries you need to take. So you know, like for that delay election algorithm I told you about, like if you had n nodes that need in this network, you will roughly take about n ln n tries. All right. Does anyone have any questions? Because I have time. I actually have time to do one more. I hope the stats major is here because it's really cool. Okay, it's not just for him, it's for all of you guys, obviously. If no one has any questions, let me quickly do the last one, okay? Let me quickly do the last one. Now, I don't want to show you how to construct it, okay? But I'm going to pretend. So let me give you this function and let's just pretend it exists, okay? And I'm like, you don't have to worry about how the function works, okay? But just pretend that I have a hash function, hi, okay? And this hash function gives me, okay, so what I mean by hash function is, right, if I give it the same values, it gives me the same output, right? So if I say h of 0, it gives me like some value. I say h of 0 10 years into the future, it should still give me the same value. That's what a hash function does, right? Okay, so it needs to be reliable. If I give it the same value, it gives me the same output, okay? But I also want it to be random in the sense that if I give it a different value, right, I should not know what that value is. Intuitively, that's what I'm trying to say. Okay, so think of a hash function, right? So this guy is a hash function. Okay, but this hash function is a bit weird. It gives me +1 or -1, and it does so with probability half. Okay. Now I want to use this hash function for something. So let's just pretend this hash function exists, all right? So again, I repeat, it's very important, okay? I give it the same value, okay? It has to give me the same output. But if I give it a different value, I cannot predict what the output is, right? Which is why I'm writing it like this. It's a bit weird, but you should, okay? Okay, so moving on. The last thing that I want to talk about. So it's related to computing something called the Gini index. I don't know, was it called Gini index or Gini index? I don't know. It's one of this. So like if you're like in data science or something and you're kind of like, if you know about this, you know, like feel free to talk about it in chat because I'm not very sure. I just know that this is the thing. Okay, and let's say you're working at like a company which kind of needs to run out like all these analytics and stuff. Okay, so let me motivate it by saying this. Let's say I have I hope you guys know what a fire hose is. So let's say you're connected to the Twitter fire hose, okay? Like or like some fire hose somewhere. So like Twitter has a fire hose, I'm pretty sure. I've actually had to deal with it before. What a fire hose is, right? It's basically just this really huge pipe of data, and there's like think of it as like, for example, a feed of like all the possible tweets being sent out, right? Now this thing is big, right? It had like there's like 1 million tweets flying like at you a second, okay? And there's no way, right, you're going to be able to store all those tweets on your hard drive, for example, or maybe like even if you had like a really big server, right, you can imagine how crazily insane you have to like buy, like how much space you would need, right, to store all these tweets and then run some analytics on them, right? So that's not very ideal, right? Let's say, for example, I have, let's just say, right, say I have m types of data, okay, that I say I have m types of data, and let's say that type 1, so if I say F1, right, this means the number of times data of type 1 happens. If I say F2 is the number of times data of type 2 happens, so Fi is technically the number of times, so this is the frequency of the ith type of data, all right? So the number of times the ith type of data happens, okay? Now, the Gini index, what it cares about is, or Gini or whatever, the thing that it cares about is the summation of the Fi's squared. Apparently this is very useful in data analytics. I don't know, right? But let's say you're like, we're talking about tweets, right? In the context of tweets, maybe there's like m types of tweets that you care about, right? Maybe you can categorize them into m different types of tweets, okay? And you want to compute this, right? You want to compute the frequency of each tweet squared and you want to add all of them up, okay? Now this is difficult, right? Because like, think about it. If I had like a million different types of tweets, right, I would need to store 1 million different counters, right? 1 million is what? It's like a gigabyte, is it? Yeah, it's a gigabyte, right? And you don't know like how many tweets of each type you have, right? So that's a lot of information. What if I had 1 billion? Then that's like a terabyte, a terabyte hard drive. Like in terms of a counter for each alone, can you even store that? It's not really obvious, right? Like how do you even do that, right? It's not, right? You need a lot of space, right? So if you use this hash function, right, the promise is you actually don't need to use a lot of space. You actually don't need to buy a gigabyte or a terabyte large hard drive, right? So if I wanted to use a counter solution, right, if I want to store an array, an m-sized array, right, the space that you need is at least, of course, omega m, right? You need at least one counter for each m type of items, right? M type of item, right? Let me throw this away and say that, okay, screw it, let's not use OM space. Let's use something like it's not really O1. Okay, it's not really O1, but you know, like fake news, right? But like, okay, I'm just gonna market to you as an O1 space algorithm, which doesn't make sense, right? Because I'm telling you, oh, you don't need to use the counters at all. You know, you don't have to buy a hard drive or anything, and this all happens because of randomization. Okay, so let me quickly show it to you guys. So the algorithm is very simple. Okay, given item of type m, so like for all the items, right? This thing is coming in a stream, right? It's coming at you. So for the next item that comes in, right? The way you process it is that when you're given an item of type I, okay, all you do is just obtain this value, h of I, okay, get h of I and add it to a counter. Add it to counter, let's call this counter x. Okay, at the end of the day, right, when the stream is done, when you're done processing all the tweets that you want, when you're done processing all this information, all this data, right, just return x squared. And that actually, this, right, I want to show in expectation is equals to summation of fi squared. Which you might think is a bit weird, right? Because like, shouldn't you expect to see 0, right? But no, that's not the case. So let me show you what I mean really quickly, because I'm actually out of time. So like, if you have to go, you have to go. It's fine. Like this is all recorded anyway, right? But for those who are staying, let me just finish it since we're already here. Okay, so think about what the random variable x is first, right? So again, what do I want to show? I want to show this, right? But let's talk about x first. So what is x? Okay, so think about what the value x is. So x is our counter, right? So how should we obtain our value x? Think about it this way. Let's sum across all the types of items. So item of type 1 to item of type m. Okay, now what should the counter's value be? It depends on the frequencies of the items, right? So if let's say I have 5 items of type 1, right, I'm going to add, and let's just say, okay, so let's just pretend for now, h of 1 is -1, let's say h of 2 is -1, let's say h of 3 is +1, right? Let's say I had 5 items of type 1, let's say I had 10 items of type 2, and let's say I had 20 items of type 3, right? Let's just say. So what should my final counter value be? It should be -5, -10, +20, right? So my final value is going to be 5, right? So because remember, again, it's a hash function. So if I see the same type, if I see the same input, I give out the same output, right? But if I see a different output, I have no guarantees, right? Okay, so sorry, if I see a different input, I have no guarantees, right? So how should we be counting this? Well, let's look at every item's frequency, right? And this guy should give me some value, right? So I'm going to apply to the hash function and I'm going to add it to the counter. If I see fi times of the same item, I know that whatever value the hash function gives me, it's always going to give me the same value. So I'm just going to repeat. I'm just going to add that to the counter as well, right? I hope this makes sense. Okay, so let's work with this. Okay, so this is x, but what I care about is x squared, right? And I want to show in expectation the e of x squared is equals to this Gini index value. Gini, I don't know. I'm sorry if I'm not pronouncing the name right. So what do we care about? We care about e of x squared, right? So let me deal with x squared. So wait, I need space. So let's talk about x squared. What does x squared look like? So x squared looks like this. It looks like this summation I from 1 to m fi h of I, okay, squared, right? Because x squared is just this entire thing squared, right? That's all I'm doing here. Okay, now what you should note is that this should look like two parts. One part is fi squared times hi squared, right? This is the part where they're the same, right? Because if you're summing this summation, there's going to be two parts. One part is where it's equals and one part is where it's different, right? So the other part where it's different is 2 times summation of I not equals to j. So you pick any two numbers, I and j, right? That are not the same. Then you have fi times fj, right? Times hi times hj. Okay. So this is looking pretty involved, but don't worry. Don't worry about that yet. Okay. Now I want the expectation. So let's just plug in our expectation here. Okay. So I know that expectation, I have linearity expectation, right? So this is just e of these values here, right? Now fi here is a constant and fij here is a constant, right? Because it's not random, right? This is given to you. Like it exists somewhere out there. It's a fixed value. Okay. So what I'm saying is that this should look like this. It should look like fi squared e of hi squared, okay, plus 2 times I, like sum across all the I not equals to j's, fi times fj, right? Expectation of hi times hj, right? Because these are the h's are the random variable that we care about, right? Okay, good. We're almost done. Hang in there. All right. Okay, so let's ask what this guy is. Right. So let's talk about this guy. Let me use a different color. Green. Okay. So what's the expectation of hi times hj? Okay. Now you might be tempted to say this is just okay. Wait. I mean, it's kind of true, but okay. So what did I say? I said that you should think of this as a hash function, right? So if I give it different outputs, different inputs, it's random to me, right? But if I give it the same input, it always gives the same answer, right? So hi times hj, you should think of them as they're independent. All right. This is not so it's not always true that you can do this, right? So this step is very important. You should only do this if you know that they're independent. So in other words, right, I cannot always write this way. The expectation of the product is not the product of the expectation always, right? It only happens when they're independent. And for now, to make life easy for us, right, let's pretend that this function is independent, right? I give it 2 different inputs, right? Because I is not equal to j. I give it 2 different inputs. It should look random to me. So it should be independent. All right. So if I have this, right, what's the expectation of hj? I hope I still have my function, right? So I kind of accidentally erased the -1 there. But because this is +1 with probability half and -1 with probability half, in expectation, this is just 0. All right? Because it's half, it's 1 times half plus -1 times half, right? So that's just 0. Okay. So what that means is that over here, this value here is going to be 0. And actually this value here is going to be 0. Okay. So what does this tell you? This tells you that this portion here, right, it all just cancels out. It all just cancels out and it becomes 0. Okay. Cool. We're not done yet. Last part. What about hi squared? Now I know that my original random variable gives me 1 or plus 1, plus 1 or minus 1, right? So with 1 I square it, and with minus 1 I square it, both become 1. So remember how this is at the beginning of the day, right? So the random variable, if you square it, like, and it looks like this, right? The final answer is going to be 1, right? Because with probability half, it gives me 1, I square it. Okay, that gives me 1. With probability half, it gives me minus 1, I square it, also gives me 1. No matter what I do, I'm always going to get 1, right? So this value here on the other hand, right? This is 0, so I don't care about the second term. I only care about the first term now. So this value here becomes 1. So what you're left with is fi squared. Which is cool, right? Because I didn't have to store m different counters and then square all the values and add them up. All I had to do was find this very wonky hash function. And all I had to do was just add, like, you know, all I had to do is just count, like using this thing. And you can see why this intuitively saves space, right? Because you're like plus 1, plus 1, plus 1, then sometimes you're minus 1, minus 1. Like, okay, it's not always true, right? But in expectation, if your function is random enough, right, what you should hope to see is that it'll go like, move up, move up, move down, move down, move down, move down, move up, move up, move down, move down, right? So you intuitively, this is very space saving. You suddenly don't need a terabyte hard drive anymore. All you need to do is just store a small counter somewhere, right? I mean, okay, you could be very unlucky, right? This thing could just plus 1 all the way and you could just get a really bad value. But the whole point of randomized algorithms is to say that, yeah, you shouldn't hope for it to happen. It should give you the value that you want instead of giving you junk. All right? So I'm actually over time, but thanks for sticking by. If you have questions, I'll stick around for a few minutes. But if not, class is over. I'll see you guys next week. And I'll cover like expected runtime of quicksort and a few other cool things. How do I split the expectation into 2 separate multiplications again? Good question. So you can, okay, wait, let me answer the other question first. Yes, you can square summations like that. I'll show you how in detail in a few seconds. Let me explain let me answer Chian first. So how do I get this, right? So you can think, okay, so if I try to be rigorous about this, okay, like you should think of this, right? Like as the summation of the 2 possible values that you can come out with, right? So this should be the probability that hi is equals to some value x and j is equals to some value y, right? And then it's x times y, right? Okay. Now, again, because I tried to make it like, I tried to simplify it. So I said, okay, look, the hash function, right, if is independent. So if you give me 2 different inputs, right, they both look random to each other. So in other words, right, giving me one input doesn't say something about the other input. Like what's going to happen to the other input, right? So they're independent events. So what that means is that this guy should look like this. So in general, no, you can't split the multiplication. If that random variable depends, right, on each other, you can't split you can't split it this way. This step requires you to say that they're independent. And I'm saying, oh, it's a hash function. We'll just pretend it is, right? So you can do this. And if you can do this, you can separate them into the 2 parts. So trust me on this. You can separate this into 2 parts. So this will become x times PRH, like I of equals to x, and this part becomes y plus y times the probability that hj is equals to y, right? But then this left term here is just the expectation of hi, and this part here just becomes the expectation of hj, which we know this is 0. We know this is 0. I hope that answers your question. If not, you can Google it. So expectation of product, and they'll tell you when you can do it, when you can't do it. Okay, Kendrick, let me answer your question. So can you square, like, you can square summations like that? The answer is yes. Let me show you. Like, I know I moved really quickly. Let me show it to you in detail. So the idea is that if I have a summation, right? Let's just say AI, right? So I like the point is that I'm summing some terms from I is equals to 1 to m, and I want to square it, right? Think about what the summation should do. So this summation, right, is the same as doing this, right? Like AI, right, times the same summation, but let me use a different index, right? Because I don't want to have like collisions when referring to stuff, right? So there are 2 parts to this 2 parts to this square, right? So think about it. there's one part where like, okay, so think of this is like A1 until like AM, and then there's like A1 until AM, right? So when you square it, right, what's going to happen is that you're going to take A1, multiply with everything here, plus take A2, multiply with everything here, plus A3, multiply with everything here, A4, so on and so forth, until AM, multiply everything here, right? There's going to be one part where everything is the same, right? Like A1 times A1, there's going to be one part which is like A2 times A2, there's going to be one part which is like A3 times A3, there's going to be one part which is like AM times AM, right? So we can take that out. So that becomes AI times AI, right? Then this from I is equals to 1 to M, right? So what's the remaining part that happens that we didn't take into account for? It's when you take the number, like for example A1, and you multiply with everything else that is not itself, right? So like A1 times A2 times A3 times plus A4 times A5, so on and so forth, right? And you have to do that twice, right? Because one time here and like one time here, right? So that's 2 times AI times AJ, where I is not equals to J. Does that make sense? You can try for small values. You can try for like x1 plus x2. What's x? So x is the counter, right? X is the counter, right? So what was the algorithm? The algorithm was you connect to this fire hose and in come the tweets, right? Then you classify the tweet. Oh, this is tweet of, let's say, type I, right? You take the hash function, you hash I, you hash the value I. Then it'll give you +1 or -1. You take that value and you add it to your counter x. So x is your counter, right? So what should you see? Every time a tweet comes in, right? X either goes up, the counter either goes up by 1 or it goes down by 1. Right? Then I said, okay, so what should you do at the end of the stream? When you're done, like, what should your server return? Your server should say, okay, x squared. Right? Then we showed that in expectation, x squared is actually equals to the Gini index. So that's the summation of the fi squareds. Does that answer your question? Cool. Right? So what's the moral of the story here? The moral of the story here, right, which I think is really cool, and I'm like happy you guys stuck around. Like the moral of the story here is that sometimes, right, you might think of an easy solution, right? Like you're at a big data analytics company, or like you're at Facebook or something, you're at Twitter, and they're telling you, I want you to compute this value because it's good for us in data analytics, right? We need this value because it shows us like the skewness of our data or whatever, the skewness of the tweets or something, right? Or skewness of your, I don't know what it is, right? Maybe in economics you use it, right? And you know, someone who's not come to 3230 or someone who's not been in this tutorial might say, I don't have a choice. I think the only way to do it is if you have a million different types of tweets. Okay, a billion different types of tweets. The best I can do for you is I give you a gigabyte drive, right? Or let's say a trillion tweets, right? Which I don't think is a stretch. Within a day, I'm pretty sure they're like within a week, they're probably more than that, right? You need like a terabyte. You need like a terabyte hard drive just to store all the counters. All right, and this is not like how to access it or anything. It's just the bare minimum amount of space that you're going to need, right? They come in, each of these types has a counter for it. You add, like every time you see it, you go to that counter, you +1. You go to that counter, you +1. Then what you're gonna do at the end of the day, when it says, okay, we need the value now, you're gonna say, okay, stop. You're gonna square it, right? You're gonna iterate through this terabyte large hard drive. You're gonna square all the frequencies. You're gonna sum it up, and you're gonna give it to this guy, which is ridiculous, right? Think about the price of like, or like the amount of money that you're costing the company, or like, I mean, I sound like a sellout now, but like the point is that it's inefficient. It's inefficient. It's a huge waste of space, right? All you really need, right? All you really need is a hash function that looks like this. And I mean, I won't tell you how to cover it. Like if you're curious, there are ways you can construct hash functions which you can look up in your own time. And if you want, you can send me an email and I'll talk about it, or I can talk about it in the Telegram group, right? But these hash functions exist, right? But the point is that all you really need is a hash function that looks like this, okay? And all it does to your counter is sometimes it just pushes it up, sometimes it pushes it down, all right? And I'm not saying that it will always give you the correct value, right? I'm not saying that it will always give you this sum of fi squareds, right? Of course, it's random. I mean, quote unquote random, right? So it could go up a bit more, it could go down a bit more. So you should, like, you know, what I should really be saying is that you're actually roughly around this value. I've not actually proven that it's roughly around that value. All I've shown is that you should see that value, right? I've not shown you that, okay, with a very good probability is that value. So when you implement this for the guy, right? Like if he says, oh yeah, but the value doesn't seem to be correct, you say, yeah, but it's close enough. So you only care about this when the values are very, very big, right? Of course, if you want the exact value, you might be asking me, hey, but what if I want the exact value? Then you have no choice. You need to buy a terabyte large hard drive. I'm sorry. You need to buy like a server farm or something. It's like store all the, like, to have all that storage. I'm sorry, you have to do it. right? But what if like if let's say your company is okay with like a close enough value, like what if it's you know like a good enough approximation, and it doesn't have the money to spend like on terabytes of hard drives, for example, then go for this. It saves so much space. I think it's mind blowing. Yeah, that like that's all I wanted to build up to today, right? But I'll show you more. I mean, okay, not this one, but I'll show you different things next week. Like quicksort, we'll talk about quicksort. We'll talk about a few other things. All right. But this is what we have to offer you in randomized algorithms. Okay. So I'll stick around if you still have questions. If not, I'll see you guys next week. Or post your questions on Telegram. I'll get to you when I can. No worries. Wow, it's the last guy in the chat. Okay, let me stop recording.